Okay, welcome. Hope that you had a good start into the new year. The good thing is we just have this last lecture, which I will use for exam preparation. And the exam itself here is on the 31st of January. I believe that's a Friday at, I'm not so sure actually, is it? Yes, it's also Friday at afternoon at civil engineering in one of the rooms there. So the important thing is you need to register, don't forget this ahead of time. And commonly I allow pen, paper, a pocket calculator and a ruler, but not a mobile phone. You need the pocket calculator to do some numerical calculations, but you cannot look up any documents or so. So if there are very complex formula, it's not about learning them by heart. I will give you these in a list of formulas at the end of the exam, but smaller, let's say, relations, of course, I expect you to know. I think that's all there is. Don't forget the pocket calculator. For this exam, you will have to use it. So if you don't have one, that's going to be a bit difficult. Are there any other questions about the organizational part? You will have 3 hours, and yeah, and I guess this is enough for what we have in mind. Let me go to the exam. I selected this one from 2023. You have probably seen the exams already. I have typically 2 to 3, sometimes even 4 main questions, and they all address different learning objectives of the course. And in the column margin, you see the points for the sub-questions and then also the sum, and they typically end up with, for example, 50 points, and then I use this to calculate the grade. So, of course, have a quick look at where most of the points are given. That indicates also where you should put the focus. So I think this is a good way to orient yourself. I always hand out after the exam the samples, the solution. So you can then, let's say, look up how you should have answered the question. But you will see that the solution is always more detailed than what I would expect from students. I add some additional details for the understanding. So don't get scared when you only had a quarter of the, let's say, text there. That is pretty normal. You will see it now here with the solution that I will give, that they are more detailed. So typically I start with the, let's say, simple venture into the topic. And here, this is about soft wing kites for airborne wind energy generation. You see the first sub-question is named 2 advantages and 2 disadvantages. And when I ask something like that, try to be concise. The more concise, the better. So I don't expect you to write, let's say, half a page per sub-question. This would be completely out of scope. You also, you can see when there are many points given, then there is typically a bit more detailed requested. So, about the 2 advantages and disadvantages, that's A, and B list 3 different types of kites that fall into this category of soft kites, and describe concisely with the help of a cross-sectional sketch through the wing. That's cross-section, how the kite works. And then last question for the 3 different types of kites. Again, key advantages over the other. And let's have a quick look at the sample solution. You see it here. This is how you could answer it. Name 2 advantages and 2 disadvantages. And then the advantages of soft wing kites compared to fixed wing kites: faster development and lower costs. Soft kites crash. When soft kites crash, you can relaunch them. They are typically not damaged because they are soft. Let's say if you don't have to be so scared about losing your equipment, you can much more rapidly redo experiments with lower risk of complete loss of your hardware. And that's why you see 2 of the prominent soft wing concepts, SkySails and Kitebauer, now taking the lead in commercial deployment. Maybe as a detail, that doesn't mean that in the long run, in 5 or 10 years, these will be the winning concepts. It only means they are quickest at the market now. So they will be able to sell their first systems, while hard wing concepts, they take longer to develop. But they might in the long term be more successful because they are more durable. It's the question of how quick you can get to the market and what is the visionary picture in 10 or 20 years. And then another advantage, is the lower risk, and not in terms of crashing, but in terms that they fly slower and that they are in large part made of soft materials. And lower risks means that they are more acceptable to the public. If you have a hard wing kite flying there, the safety measures for the on-ground, let's say, infrastructure and people are much higher than for soft kites. Now, if you have questions, just ask in between. Also, soft kites are more mobile. You can pack them and unpack them much quicker. And that's also, let's say, where the entry market will be. We can see it now. So the first systems that have been sold, they are for applications where you need to quickly move around with your generation equipment. And the lower cost of the final product. So these soft kites cost a lot less. But you need more of them. So remember, I mentioned that we see a shift from capital expenditure at the start of an installation to operational costs, because you have to replace these kites more frequently. So you see, I say a lot more than is expected here. It's enough if you write it down in a very concise form. Okay, and then disadvantages of soft kites. I mentioned some of them already. Lower durability. To more frequently replace. The full automation of launching and landing is more challenging because the kite deforms. A ram air wing is just like an air mattress on the ground. The leading edge inflatable kite does have a inflated frame, so it's better for handling. The ram air wing is horrible for handling. That puts more challenges on this automation aspect, this one here. And the lower performance, and I think we will get into that in the next question, so let's leave it at that. And the limited depower capability. You remember probably that such a wing, when it flies at a negative angle of attack, so inflow coming from here, is horrible because it can rapidly collapse. Maybe let me give you one detail here, because I mentioned this in one of the last lectures. So if this is our wing, and let's see, wind velocity here as a vector, and we are reeling in. So this is our reeling velocity, Vk, then remember that V wind minus Vk is Va. So you see that the angle between this line here, the apparent wind speed, and this line, if we just draw the parallel here, this would be the angle of attack, alpha. And you see that, for example, if there is a strong wind gust, so if this wind velocity here suddenly becomes like this, then you see that this VA quickly more aligns with the chord line, and if you bring this to the extreme, you can even have negative angle of attack. It's just now not possible because I drew the wing like that. But imagine if it would have been like this. Here, this, and this would be the chord line, and you see that already here you have, in this case, you have an angle of attack of 0. So a wind gust can quickly change the relative flow kinematics at the wing. And that's why they are extremely prone here to negative angle of attack. Any questions? Yes.
And why is it mostly a problem for fixed wing kites?
For soft wing kites.
Oh, okay.
Disadvantages of soft wing kites compared to fixed wing. A fixed wing kite does not care so much about negative angle of attack because it just influences the aerodynamic lift. But a soft wing kite would collapse. If you have inflow, relative inflow coming on top of the wing, you can imagine that this just kind of presses down the center part and the wing can flip inside out and collapse. And we have seen this in practice, so this is one of the, let's say, one of the modes where you need to be very careful when you reel in a depowered way, so with low angle of attack, and then you have sudden wind gusts. That can happen, that they collapse your wing. And then you don't lose the kite, but the kite will crash and you have to re-unfold it. And that is again an issue for the automation, of course. Okay, then let's move on. Then the next question, sub-question was soft. Wait a minute. Okay. This is the text and this is the image. So I wanted to get from you cross sections of different soft wing kites and explain this. And of course, we have the leading edge inflatable kite. You have seen this many times. It has a recirculation zone here always, simply because this tube always leads to some flow separation, so this is the point of separation. And the flow recirculates here, driven by the shear flow along the suction side. At high angle of attack, you will get flow separation also creeping in from the trailing edge on the suction side. Sorry, this is the pressure side, this is the suction side. Then the next concept is the ram air wing. Sky sails, for example, is inflated by the stagnation pressure here at the inlet. Then you have single skin kites, where we basically take away the tube and replace it by a preformed open leading edge. Important is that for this type of kite you need a lot more bridle lines, because you actually lose the inflated frame. that actually is used as a substructure for the canopy. So this, instead of this frame, tube frame, you will have a lot of bridle lines. This is also how paragliders are constructed. And then we have this more special type here, the rotating balloon kite, that uses the Magnus effect. So by applying a rotation, you distort the flow around the cylinder, and that creates the Magnus effect. Yes.
Is the Magnus balloon, is that not a fixed wing kite, or is that?
It is this is a soft wing kite, or let's say we call it soft wing because it's a balloon. It's made of fabric. You could make it also fixed, and the fixed version of the Magnus cylinder is, for example, used for ship propulsion now. So there are ships that have these cylinders on deck that rotate, and they are used as sails, basically. But for a flying system, it is extremely likely that it will never be fixed or made of solid materials. They are too heavy. So these are the 4 types, and what I just explained in words also written down here. So you can actually download these exams from Brightspace. You might have done already with the sample solutions to go through this. And the more recent exams are also more relevant. Maybe that's also logical. I've changed the scope of the course over the years that I taught it. So start with the recent exams and work your way to the older exams. Some of the older exams are not so relevant anymore. Yeah. And then there was a last point. This one here. For each of these 3 types of kites, 3 types? Okay. I counted 4 here. So meaning here I give 4, but it would have been enough if you stayed 3 kites. So this one here is, I would say, an add-on, not necessary. But if you know 4, then just give 4. Okay, so the LEI kite, they have a well-defined platform. That's the platform, actually, the shape that you see in projection, because of this frame. So once pre-inflated, you can handle the wing on ground. You can move it around, you can turn it, you can put it in a launch shape. You cannot do that, for example, with a ram air kite. A ram air kite is just a piece of cloth which you need to inflate before it has shape. And this inflation opening at the, I should mention this inflation opening here, of course, once you remove the inflation device, this kite will become a, let's say, untangented piece of cloth again. I'm not sure how paragliders do that. I think they pull this piece of cloth into the air so that it catches a bit of air. It's a specific technique, but of course, to automate that is difficult. Oops, sorry. What happened here? Hey. Yeah. And ram air kites, they have the advantage that their cross-sectional geometry is very well defined and also optimized for aerodynamics. Now this cross-section, so what you see when you cut through here, is not very optimal because of this recirculation zone here. So you have the flow basically going like this. And this recirculation zone here is something that an aircraft aerodynamicist would never tolerate. But we tolerate it because Aerodynamic lift is not everything, so it's much more about compromises. Also in ground handling. And the single skin kites, maybe as a last point, they are reduced to the bare minimum of structure, so they are extremely lightweight, which is why they are used for lightweight for light wind sport applications, for example in the Alps for snow kiting. You have a little wind typically. You also need to carry this thing somewhere, so you want it to be lightweight. But the automation of this type of kite would be hard, right? Because it's again just a piece of cloth. You don't have any structure in there that defines it. And the cylindrical balloons, based on the Martin's effect, they have extremely good lift properties. But maybe this is a bit a special topic. So the lift of this rotating cylinder is much higher than you can go with any conventional airfoil. But they do have a lot of drag, as you can imagine also, so the lift to drag ratio is not so great, but the pure lift is unmatched of these devices. That's the advantage. Are there any questions regarding this? So this is a typical question where, yeah, you just need to know these things and study that beforehand to be able to answer. Then the next type of question, let me see here. This is now more an analytical analysis, the retraction of a kite during a pumping cycle. So how do we pull in the kite? And I described this here first with a bit of text. So here in this setting, we reeled out with an average elevation angle of 30 degrees. So it's not about only retraction here, but I give the context of a pumping cycle. And I also give a few values here that you can use to do your analysis. First sub-question is then here. Here, when reaching the maximum tether length, crosswind maneuvers are discontinued. The kite steered into the plane spanned by the wind velocity vector and the vertical axis, and keeping the tether length constant. And then I ask you to calculate the elevation angle of the kite when it reaches its static flight state. And for this, of course, you need to conclude, okay, static flight state, that's something we discussed in the theory lecture, and that's the flight state when nothing moves. So the tether length is constant, the kite is just standing there in the air, and that's something you can easily write down. Get some equipment here. So that's a relatively simple question to start off. Not too difficult. So we have the wing, the tether and the ground anchor. We are looking for this elevation angle, I believe I asked. Yes. And you remember that there is no mass given. Let me check. There is a mass given. Yeah, but in this sub-question, assuming that the mass of the kite is 0. So that makes it a bit easier. Meaning there must be a perfect equilibrium between the tether force and the aerodynamic force. That's that one, Fa. And because we typically assume that the wind velocity is horizontal, so parallel to the ground, you can decompose the aerodynamic force into a lift and a drag component. Here's drag, here is lift. And from this, let's say, force geometry, we can easily see it's beta again. So beta, so tangent beta is a lift to drag. This is something that we discussed also in the beginning of the course in lecture 4. And from this you can further, let's say, derive, you know, that lift is 1/2 rho CL reference area V wind, because the kite is not moving. Write down K0, static flight condition, squared. That means this part, and this part is the same for drag, right? That's basically the same, only here CD, the same, meaning this is CL divided by CD. And then you see that I gave you these numbers here. So to answer this question, you know that tangent beta is 0.25 divided by 0.2. Sorry, which is, let me just open maybe the sample solution, because I've written this down here. Yes, exactly. So this is 5 divided by 4. And in this specific case, 1.25. I think I even, sorry, let me see here. I put some of these numbers into the appendix. No, I did not. Okay, into the list of formulas. So I did, this is one of the examples where you do need the pocket calculator for. So this is 1.25, and then when you calculate beta as arc tangents of 1.25, you get to beta is 51.3 degrees. Huh? So that means the kite, and maybe let me just draw this. We are here in an X wind and Y wind diagram. So we started to reel out at 30 degrees from here to here. So this is 30 degrees. And then at the end of the reel out phase, the kite would basically fly towards this point, and this is where you would have 51.3 degrees. And this rise here simply happens because you stop the reel out speed here, stopped flying crosswind maneuvers, and then the kite is steered towards into this plane, depending on where it was during the crosswind maneuvers, and then it will automatically fly to this point and stop at 51.3 degrees. Okay, and then I asked to recalculate the elevation angle by using the value of the kite mass. Yes?
What is the L and the D in the
here?
blue ground?
This is lift.
In the blue ground.
In the blue. Sorry, you can't see that. Let's see now. Here is the L, so that force, and this is D. So it's simply the decomposition of the aerodynamic force into drag and lift force. And drag force is always aligned with the wind, with the apparent wind and in case of Vk equals 0, it's the wind speed. Well, the lift force is always perpendicular. And why is the lift force in this plane here? Because the drag force is in this plane by definition, and because the aerodynamic force is in this plane, because the tether is in this plane by definition. This is how we set up the problem. And when this force and this force component and the main force is in this plane, the third component, or the lift force, also has to be in that plane. So then if we take into account the mass, we need to expand this equilibrium by the gravitational effect. The way you do this is simply adding here, or subtracting mg. And you see this here. So what you do need, so we need basically this lift to balance mg that of that size to basically, you can put that here, so that the force equilibrium then is Fa plus mg plus Ft equals 0. And that's the static force equilibrium including mass. Lift plus mg gives, sorry, I went one step too fast, because Fa is of course lift plus drag. So lift, this L here and this mg is in the same direction, because that's how you that's how you can then write it as a scalar subtraction, and then d is perpendicular that component. Yes.
How do you know for this problem that the wind is?
It's a good question. Let's have a quick look. I hope that I wrote this down here. Did I write anything about the wind speed?
It says in A it says something about the plane spanned by the. I'm not sure if that means that it's horizontal.
Yes, that is true. It's a good observation. I should add that. You're right. So if I don't specify it, and in the main, let's say, part of the course, I assume that it's horizontal to the ground, then it's actually very safe to assume that we apply this condition here. If I would have also used the vertical component of the wind speed, I would definitely have mentioned that here. Yeah, sometimes I miss little details like that to specify, but you're right, it should be stated here. But to come back to this, so Fa is the sum of two components, lift and drag. Then we add mg in the same direction as lift, and then Ft in this direction, and the sum of these forces should be 0. Is that clear? This is simply a static force equilibrium here. And going from the force equilibrium to this, we actually make use of the geometry here, that lift and gravitational components are in one direction and drag in the perpendicular direction. And then we see again this triangle. So let's say, in this case with mass, this would be lift minus mg. Right? Good. And if we insert this, let's have a quick look at the numbers. Mass is 20. For the gravitational constant, we assumed 10. So 10 times 20. But let's not do that on the board. Let's say you see it here. So I calculate this mu because indeed we for this problem here, we cannot reduce this to CL and CD, right? Because we have here this mg term. So for this problem with mass, you have to fill in all these numbers. You cannot work only with CL and CD. You do need CL and CD, but you also need the density of air, the surface area of the kite, and the wind velocity. Right? And all these dimensional properties we bundle here in this mu term. This was also in the lecture. And using the values from this table 1, you can calculate that. And you see that with mass, you get to a lower value of the elevation angle, 45 degrees. Any question? It's clear, right? And then, let's see, starting from the static flight case state of the massless kite. So we actually go back to massless kite, 51.3 degrees. The tether is then reeled in with the reeling factor of -1. That means we reel in with the same speed as the wind speed. And then you are supposed to calculate the lift to drag ratio that the kite would need to have to fly back towards the ground station directly from this position without changing the elevation angle. So what do I mean with that? What I mean with that is once the kite has moved here, I want to know how can I now move it back on this trajectory by setting a reeling factor f of -1. So this is Vk divided by V wind, because there is no tangential component. This is the radial component Vk. And what lift to drag ratio do we need for this? And for this, maybe first draw the velocity and force triangles during the retraction and label all vectors and angles. And maybe let me just do this first. Okay. But okay, I have a proposal. We do it actually in the way I set up the sample solution. So this is the second part here. Draw the velocity and force triangles. The first part is calculate the lift to drag ratio. And for this, you see that I gave you a formula in the listing here at the end. So this is how you can compute the elevation angle for a non-maneuvering kite, so no tangential velocity, valid for all values of f. That's the formula. And from this formula you can see that we have a value of, so we say beta is 51.3 degrees, and then we use this formula, cosine beta equal, and we have a real a factor for f. We say f is -1. So we can already take this into account. So if we set here -1, we basically 1 minus -1 squared is 0, meaning this term e here falls away. Square root of 1 is 1. See that we get to 1 plus f, so minus e squared, and then 1 plus e squared. Okay, so what do we do with this? We probably multiply this up. Plus e squared, bracket 1 minus e squared. And then we need to factor these numbers in. Let's see how I did that. Maybe let me just write it out. Cosine beta plus cosine beta e squared equal 1 minus e squared. Then I combine this one and this one. So this gives e squared cosine beta plus 1 equal 1 minus cosine beta. See, is that right? Yes. And then I just divide. So this is 1 minus cosine beta divided by cosine beta plus 1. And when I plug in the values, can you read this? When I plug in the values 51.3 degrees, I get to e squared is 0.213, and then this leads to e equal 0.48. It's actually plus or minus 0.48, but the negative value doesn't make sense. So here you see this is the lift to drag ratio that we would need, which is a very low one. So you need to depower the kite to this lift to drag ratio to be able to pull it back in on from the point where it actually stopped. Okay, is that clear? Good. And then for the next sub-question, no, for the second part, we need to draw the diagram. So I draw here the situation that I requested here, exactly the situation of retraction at 51.3 degree of elevation angle. So that's what you see. This is my best guess of 51.3 degrees. So if you do this in an exam, take a ruler and measure it exactly, because then you make sure that also these arrows here come out correctly. So what you see is we have here the retraction velocity Vk aligned with the tether, meaning we have here the negative kite velocity here, and what was stated in the question? Let me see. Here, reeling factor of F is equal -1. What does that mean? F equal -1 means Vk divided by V wind is actually 1 or -1. But that means the wind velocity and the kite velocity must be the same length. And the way I constructed this here is just taking the, how do you call that, this device to draw circles. I'm missing the word. I took this and just draw here a horizontal line. So this is V wind and this Vk. So by indicating this circle here, you basically show that the length of this and this vector are the same. And then once you have the wind vector here and the negative kite vector, of course you can apply this equation. VA is V wind minus Vk. So you basically add V wind to V minus Vk, and then you get VA. So we can draw VA. Once we have VA, we know the direction of the drag because it's always aligned. And so drag is always parallel to VA. We also have, we have FA, the aerodynamic force. And basically you just define a length here because it was only about the, let's say, qualitative drawing. We define a length here for FA, then you draw the perpendicular line, then you have the drag force, and you draw the other perpendicular line, and you have the lift force, and this is how you can actually draw this. And you see that if you take this length from this diagram and divide it by this length, you actually end up with the 0.48 that we calculated with the formula. And why is that? Because this is actually a truthful drawing of this situation where F is -1, because we use the circle here, the circle construct, to have the same length of Fw and Vw and Vk, and because we had a good estimate of 51.3 degrees. So these are the two, let's say, ingredients to make that diagram correct. This angle here and the same length of Vw and Vk. And then if you construct this, you should end up with 0.48 as the ratio of lift to drag. And that's a very low ratio, aerodynamic lift to drag ratio, to be able to fly down on this trajectory. Good, and then let's see, there was probably one more question. Here, derive an expression for the minimum steady state real factor F star min, and use this expression to further determine the associated maximum steady state elevation angle. So the question here is what's the lowest possible value for F min? And then remember to look into this formula, and you see here that there is a square root, and the square root should never become negative. The radicand here should never become negative for a real valued result. So we can have the condition that this term here should be larger than 0. This is something we explained in the lecture. So 1 plus e squared, I think it was 1 minus f squared, should be larger or equal 0, and the equal 0 is probably the extreme condition. So where does this bring us to? E squared 1 minus f squared should be larger than minus 1, which gives e squared larger than minus 1 divided by 1 minus f squared. Don't need the bracket here. So here we need to, and we can already see that, let's say, when f gets very large and negative, then this will be a large number. Let's look what I wrote in the solution. I think it's more safe. Yes, I went a little bit different. Did I make a mistake here? No, that's it, right? Okay, my mistake. We need to solve for f, not for e. That's of course important. Changes a little bit the course of this calculation. So the question was for the minimum f, meaning we go for that one still stays the same, 1 minus f squared larger than minus 1. Then we need to divide by e, 1 minus f squared larger than minus 1 divided by e squared, which we can continue to f squared smaller or equal to 1, that's right, plus 1 divided by e squared. If you see a mistake, tell me. So we expand by e, giving e squared plus 1 divided by e squared. That means that f should be smaller than the root of this expression, which is probably also what I have written down here. Yes. But a bit more correctly. So because we have a square root operation, we have to say same root minus. So f can be in between these two bounds. One can see already that when e becomes very large, this actually converges towards 1. But it can never be larger than 1, which is actually what this, so for small e, you could see that this term here gets larger than 1, but that's not possible. The real out factor can never be larger than 1. So the upper bound is actually 1. But the lower bound is this one, and did I yes, and the next question was the maximum steady state elevation angle beta max, and for this you simply insert this expression into the beta equation. What is the beta equation? That's this one here. So if you plug this expression into this one, then you get to this derivation. And this has an interesting side note, I mean, maybe this is something you can read through at home, but that was not part of the question anymore. You can find actually a geometric relation that this beta max is actually can be related to this angle gamma, which is the angle between the lift vector and the the aerodynamic force. So if you know the aerodynamic properties of the kite and you draw this triangle like these force components like this, you can. That's not how the kite would fly. It's just geometric exercise. And then you flip this over to this side, and then here with this angle gamma, you see that this is the maximum elevation angle. And what's interesting is if gamma goes to 0, that actually means that we go towards an infinitely large lift-to-drag ratio. So for an infinitely large lift-to-drag ratio, the kite would actually fly towards the ground station from perfect upwind, which is a little bit absurd if you imagine this. So for a perfect kite, meaning with infinite lift-to-drag ratio or 0 drag, once you reel in with the minimum possible reel-in factor, the kite would really fly over to a 180-degree elevation angle and then return to the ground station. I'm sure in practice you would not observe this because there is no infinite lift-to-drag ratio. But as a, let's say, theoretical exercise, I think it's pretty interesting. Let's see if there was. Does that raise any questions, except the one that I asked myself? No? Clear? Then the next question, let me see. Go back here. Yes, so that was what we just answered. And that had 8 points. You see that this is, so this analysis here was quite highly valued. Also, by the way, the elevation angle for static flight with mass also had 8 points, so you can see that there was more math involved. And then this question here, E, considering an arbitrary initial position. So now, initial position at the start of the retraction phase, let's say here, just any other position, then and some normalized radial kite speed, F, or reel-in factor, formulate an expression for the normalized tangential speed beta during the retraction of the kite. And this should only include dependencies on beta, the aerodynamic lift-to-drag ratio, and the reeling factor. So how do we do this? Let me take a peek myself. Okay, that's this one. So I gave you for this some help. Ah yeah, here. You see it here. The tangential velocity factor. That is the key for this. So we first set the specific flight conditions we are in. So we put the azimuth angle to 0 and the course angle to 180 degree. Remember that the course angle is the angle of the kite. Let's say if here's the origin, this is a course angle of 0. This is a course angle of 180 degree. That's the theory of spherical coordinates. So in the reel-in phase, we always use a 180 degree course angle because the the kite is basically retracted in this way towards the ground station. So it always points upwards, or let's say forward. Is that a good explanation? No. In spherical coordinates, remember if this is x wind and z wind, so and here is my radial direction. So if I'm in that plane here, where phi equals 0, then a kite pointing in this direction would be 180 degrees. This would be 0 degree. So basically, depending on where you are, this would be the 180 degree course angle. And we need to set this. When we set this in this equation here from the appendix, you see that a number of terms drop out. I'm not doing the math here now, but you basically get to this formula that looks a bit complicated at the beginning, but you see that sine beta squared and cosine beta squared, you can of course collapse to 1, and then 1 minus 1 as 0, so actually all this here drops out. Then you have 2 squared terms, and the square root of that is of course the radicand, then is of course the term itself without square, which is this, and then minus beta. So this relationship here is giving us the tangential flight speed, non-dimensional, so beta, just as a reminder, not beta, gamma is Vk tau divided by the wind. This is the law of motion of a kite in quasi-steady flight mode. And the next thing that you would need, because this just says depending on a certain elevation angle, beta, and a certain real-in factor, and a certain lift-to-drag ratio, we have a certain speed. But there is one more relationship, and that's this one, and that's purely kinematic. And I draw this here. It's not very complicated, but so x wind and z wind. This is my radial direction r, and here is my Vk tau. Then, and here is my angle beta. We can actually write radial direction times beta dot. So the time derivative is Vk tau. This is a simple kinematic relationship, right? Here is right angle. R times the radius times the angular speed is actually the tangential speed at that point. And then if we divide this by the wind, so we have R beta dot equal lambda times V wind. I think that's the relationship that I wrote down here. And now if you combine this, or you plug this lambda in here, then you see we get to this differential equation, and that simply gives us the time derivative of the elevation angle as a function of let's say the state variables of this problem. This is something you could integrate, for example, simply integrate, and you would get the time law of motion. Maybe let's see what the rest of the question was, because I forgot this already. I think that was this question. I just expanded this here with some additional.
Yeah, about the expansion, I don't really understand how they come to the last part, so what they call cosine exactly over there.
Mm-hmm.
So formula 22. How do they come to that?
Yeah, that's a good question.
Myself, but it's actually quite hard.
Yeah. I didn't ask this in the exam. I think I went a little bit over the top here in my example solution by finding this out, because I thought, okay, if we have this law here for beta dot, we could say, where is beta dot equals 0? And then we should have again the static condition. And by setting beta, indeed, if we set beta dot to 0, we should get to beta star, and beta star is the static equilibrium case. So beta dot equals 0 means that this term here should be 0, and that is actually this starting equation. And then we do a bit of math. Okay, here we simply just replace sine by cosine. Then we bring everything to the other side. And
How do you come to the denominator?
here, yeah, now you are asking very difficult questions.
It's not necessary.
It's not necessary. Definitely not necessary.
But the steps in between are, I think, quite
Left out. They are certainly big. I don't know myself, no. But I mean, I'm pretty sure it's correct, because you can solve this equation and you get to this solution, which is the steady state retraction law. Maybe I just left them out because it was not necessary here for the solution. But you're right. I mean, that would be a bit too big the jump. And then formulate a constant force retraction strategy using the expression of Ft from the list of formula. List of formula gives us this term. And what would be a constant force retraction strategy? That would mean we want a law that keeps the left-hand side here constant, while, for example, our beta changes. Let's see what I wrote. Yes, this is what I wrote. So I just take this equation, this one, and solve it for beta. And then I get this expression. And on the right-hand side, I have only constant properties. Ft, something that we set. Let's say the lift-to-drag ratio, we always assume constant in these analyses, but for sure in practice it will not be constant, but for simplicity we set it constant. And on the left-hand side, we have the angle beta that will change, and also the real-in factor that we can modulate. So with this term, you have a relationship between beta and f based on a constant right-hand side, and that you can use actually for real-in. That's the solution. That sounds like a simple question, but of course you really need to relate it to this force law. Any other questions? I mean, this is what you can expect. I can already tell you about the exam that's upcoming. that will be in the same style, of course with different types of problems, but I have, let's say, a first question that is very much focused on the first 3 parts of the 3 lectures, so which is more about knowing things, let's say, knowing different types of systems and the layout of systems. And then there are 2 or 3 other questions that are more about the theory part, in a sense of what we just went through here, where you have to draw some diagrams, vector diagrams, and then also do some analytic analysis. And for that you do need the pocket calculator. Yes?
Will there be some questions about the history as well?
I can already tell you there will be some historical references, but never, of course, never too much, right? This is a technical course. I use the history mainly to draw parallels between what was there and what we use now. It's not about just some historical concept that is not of relevance. But for example, some of the old or some of the historical kite applications or even details that are also visible now in airborne wind, and that is something that you can expect that I will ask for, let's say, correlations. So that's my plan for the 31st. Is there anything else you want to know? I think it doesn't make sense to look at another exam now, because this was pretty representative. I will have more than 2 questions. I know it's 3 or 4. But it's such that you can easily do it in 3 hours.